Hello, good morning. So my name is Dmitrijs Milajevs, and I'm from Queen Mary, University of London. And this is a joint work with Dimitri Kartsaklis from University of Oxford, Mehrnoosh Sadrzadeh, and Matthew Purver, both from Queen Mary. Okay, so this talk will be more like about semantics, so we will look how...
Closer to the microphone.
Okay, like this.
No, you don't have to do that. Somewhere in between.
Okay, good. Is it better now? Okay, so, we want to model meaning of words and sentences, so how do people do it? And if we look to formal semantics, what do we have? We have our individual constants, which will be symbols. So we have John, which we can write as J, and Mary as M. And then we will have our predicates, which are things which we will apply our constants onto it, and we will get a sentence. So if we get a sentence, Joe so Mary, grammar will tell us how we compose the meaning of the sentence from the pieces of our symbols. That's main idea, and it works pretty well, right? However, in this setting, we cannot really say relations between John and Mary, like, are they similar or not? They're completely distinct symbols. So distributional hypothesis is saying that, okay, actually we can measure the similarity between things, and we can say one is more similar than another one. And we want it because probably John and Mary, even though they're distinct, but they're much related to each other than idea. And what this work is about is extending this idea to sentence level. So how can we say that pair of sentences are similar or not? And there are a lot of problems. Well, you can get different words. There's word order issues, and also our verbs can have different properties, and so on and so forth. So how it's usually done, the standard old school distributional approach, you fix some target words, you get a corpus, and you look what are the words around it, and you build a coherence matrix. I guess everybody familiar with it. More or less, and then if you get this vector space and you project it into dimensional space, you can see that indeed the words which have similar meaning, they occur together. So you see boy and girl are close to each other, blue and pink are next, and their colors. And just for the sake of demonstration, you can also see relations here. So woman to man is similar, is kind of what mother to father is. A different approach to this distributional hypothesis is coming from the language modeling problem. So there, if in your training corpus you see a sentence, the cat is walking in the bedroom, then you want to assign your probability mass, like being very smart, and and you should think that, okay, the unseen sentence, a dog was running in a room, should probably get, is equally probable because of all the words share the semantic and syntactic properties. And that's example taken from Benjo, from his paper on neural language models. After that paper, there was a lot of work how to scale these neural methods to larger corpus and larger dictionaries. And recently, Mikolov got very breakthrough, and he looked at it not only from the language modeling perspective, but also from this kind of distributional semantics way. So when the word vectors are really the thing we want to have. Okay, that was an overview of the history. So let's now go to the tensor-based compositional approach. So there, we want to compose our word vectors And we need to look in. If we go back to to formal semantics, the verbs was a predicate, and predicate takes arguments. So we want to mimic this thing, and thanks to Baraki, we can do this trip from predicates. We can go to linear maps, and from linear maps we can get to tensors. And tensors is just the generalization of matrices, right? So they can be in multidimensional. And once we got this sentence like John saw Mary, we apply the tensor of we apply vectors from John and Mary to it. And how we do it, we will see later. The key point is here, now we need, once we have this tensor for verb, how we actually obtain it. And there are two ways to do it. The first one is relational. So from a corpus, you retrieve all the triples, verb, subject, object triples. You do chronicle multiplication of them, so you get a matrix, and then you sum them up. Another method is even simpler. You just take the multiplication of the verb itself, and that gives you a matrix. Okay, so we kind of know how to represent verbs now in our settings, how we can compose things. So in 2008, Mitchell and Lapata had a paper when they used pointwise addition and multiplication, and that started all this compositional distributional semantics approach. Then in 2011, Greffenstadt and Sadrzadeh, they came up with a categorical composition when they actually had these different verb matrices, right? Then that method was extended by the methods inspired by quantum mechanics. So you get this copy object and copy subject ways. And the later work is Frobenius addition, multiplication, and outer product, which is, you can basically see it as a mixture model of copy object and copy subject. So in addition, you will sum up these two vectors pointwise. In multiplication, you will multiply the values. And for Frobenius outer, you just do, again, Kronecker product. Okay, let's go to the experiments now. For the experiments we chose three vector spaces. The two of them are traditional coherence-based. So GS, which is based on BNC, very small corpus. We lemmatized it, we choose 2,000 dimensions, and we applied PPMI. This method was heavily used in the literature and was quite popular. The second one is using a larger corpus. It also uses the SVD to minimize number, to get smaller vectors. And the last one is these neural embeddings by Mikolov, which we didn't train them. We just took them from the website. And our goal was to compare. Okay, here we got vector spaces which were kind of built using knowing what you're doing, and they proved to be useful. And we just take neural vectors, and we want to compare how do they behave. So the first task was this ambiguation task, and it's as follows. So you get a sentence, system is specification, and we assume that meets here can have two meanings, satisfies and visit. But in this context, satisfies is much dominant sense than visit. How we do it, so for every possible sense, we just add the context, and then we measure the similarity between these sentences. So between sentence system is specification and system satisfies specification. And if it's the sense of the verb, the sentence should be similar. However, if you just look to verbs here and theoretically try to measure the similarity of these words, satisfy and meet should be similar, and visit and meets should be also similar. So what we're really testing here is the compositional bit. So we got our free vector spaces, and we got quite a lot of methods. Our baseline was just looking to the verbs, and what we can see from the verb baseline that the neural word vectors gave the worst result, but that's what you actually want to achieve, because you cannot really distinguish between that sense. Surprisingly, the SVD vector space got very high score. Then neural vectors, they gave the best result, and it's almost state of the art, which is 4.7, I think. Again, as you can see, the copy object is the best compositional method. It might be because object is actually what carries the disambiguation. And unfortunately, not always the mixture models behave as good as just copy object. So they introduce some noise. The second task was sentence similarity. Yes? The green is improvement over verb-only baseline, and red is lack of improvement. So if the model behaves worse, then it should have been. So that basically means if you compose things, you get worse result than if you just look to the verbs. Okay, is it clear? Okay, so the sentence similarity. Here you're already given sentences, and you need to say how similar they are, and again, try to correlate with human judgments. Here the story is a little bit different. So first of all, verbs are already different, and verbs carry quite a lot of meaning, so that's why the baseline is giving much higher results. If we look to standard, like pointwise composition, these methods give higher result, and categorical composition methods couldn't actually keep up in all the models, and the SVD reduced couldn't even get the baseline results. Okay, so we carried out with two other experiments, and which are, so far our sentences were really handcrafted, and we knew what is the subject, what is the object, they were very short, but we wanted to scale it up to apply to some real tasks. Unfortunately, we couldn't do categorical composition, so we stick just to pointwise addition and pointwise multiplication. So the first task was the Microsoft paraphrasing, where you get pairs of sentences, and it said, is it the second one paraphrase of the first one, and how we did. We were computing the similarity of it, and if the similarity is greater than a certain threshold, then it's the paraphrase. So we split the data on test set and training set. Surprisingly, so neural vectors behave best here, gave us 0.73, and state of the art is 0.77. So that was really surprising that such a simple technique yielded such a good result. Unfortunately, if you look to the distributional vector spaces, the numbers are lower. That might be the case because, like in this case, BNC is a much smaller results, and we couldn't, and there was, and we got the data sparsity issue. So the second task was dialogue tagging, which we took switchboard, which is a corpus of telephone conversations, and their utterances are tagged, like it's a question, it's a statement, and so on and so forth. And what we did, we got the vectors for an utterance, then we put them all together, we run SVD on utterances, and to do the classification tasks, so to label an unseen utterance, we were using K nearest neighbors classification. And here, again, neural vectors gave best result, and So here we had a choice whether we should lemmatize a switchboard or not. And if you do lemmatize, the numbers drop. So that suggests that actually morphology is really important for dialogue processing. And we did it because like BNC and UKVec are not big enough, and we get sparsity issues here. Yes. However, if you in the previous work we got similar results for neural nets. So we got 63 as well on a coherence-based vector, but using Google Books n-grams. So now we need to put ourselves into like what others did and compare to the previous work. And I guess all of you read this great paper by Baroni when don't count, predict, when and that's the part of it saying that context prediction models obtain a thorough and resounding victory against their coherent-based counterparts. So it was very strong statement, which we kind of partially support, I think. So, but if you read other papers, like Levy is saying that, okay, analogy recovery is not only restricted to neural word embeddings. A similar amount of relational similarities can be recovered from a traditional distributional word representations. Okay, so if you treat distributional approach correctly, you still can get nice results. And if you look more for the literature, like 2 years ago, Black and Lapata, they have a study comparing distributional vectors with neural vectors, and what they're saying that shallow approaches, shallow meaning the distributional, are as good as more computationally intensive alternatives on phrase similarity and paraphrase detection task. But that might be due to the case that they use different model, different from Mikolov. Okay, so now we're still thinking like which paper we really belong to, which do we support with our stuff. So we were looking to lots of our experiments, and we wanted to generalize something. So what we get here is, okay, the vector space, the task, and the plus, green plus means that in half of the compositional methods, we got an improvement. So the bold value means that actually the vector space gave the best result. So it's funny enough that the SVD space managed to give the best result, which none other model could catch up, but it was failing in the other compositional methods. If you look to the smaller BNC-based vector space, because it was so small and we lemmatized it, we couldn't really perform well on the large-scale task, like paraphrasing and dialogue tagging. However, the neural vectors, it's a large vocabulary, and they managed to perform everywhere nicely. So what we can say is, to conclude, and I think that's quite important in the compositional community. So it's much more important to think how you compose things as opposed to what actually you're composing. So, and people can start thinking about the compositional ways and don't really care that much, is their vector space good enough? Is it tuned to the maximum? Unfortunately, the tensor-based compositions don't yet outperform simple addition and multiplication, as our second task show, where no task could match addition. So neural word embeddings, as you saw in all the tasks, they gave really stable results. And it's a very nice way to just take it and use as baseline. So once you implement some other method, compare them to neural embeddings, it's easy. Software is there, vectors are there, so it's just a matter of downloading the stuff. So, but these vectors might be good not just by their neural origin, but because they were trained on the large corpus. And that's what we are kind of working on in our current work. Thank you very much.
Thanks for very nice and very useful talk. I'm just wondering, okay, it seems to me, just what you were just saying, right? So your results are fairly convincing that the neural network embeddings are more successful, but otherwise, for most compositions, not even addition is actually seems to be more effective than all these more sophisticated methods that have been proposed. Now, addition has been around for years because actually addition was developed already by the LSA people, you know, Kinch and Landauer, et cetera, so it's been around for 20 years. So I was wondering if you could comment a little bit more about the fact that this tensor-based composition doesn't really seem to be getting anywhere.
Oh, maybe that's the wrong message. No, you shouldn't take it away. Okay, let's look to the numbers. Okay, in sentence similarity, in this data set, it might be the case that verb actually carries a lot, as we see. And then the arguments, they don't carry a lot of information. And these data sets, they don't really test word order. So John saw Mary, and Mary saw John will be completely similar. And while these categorical composition methods, they treat word order correctly. So you will get different vector representations. So maybe there should be developed a special data set which tests specifically word order. If we look to this disambiguation results, well, that's kind of improvement, right? We get 0.15 and the copy object gets 0.46. So it seems that for this task, as I said, the categorical composition would be a choice. Did I answer the question?
Well, this is a case of carefully chosen task and with carefully chosen sentences. I mean, if you go to the paraphrasing, for instance, again, you get the same.
Yeah, but in paraphrasing, we didn't do categorical composition yet. Because we simply can't do so far. But that's work in progress.
Just to clarify, if you go to your conclusions slide, so in the second point, when you say tensor-based composition does not yet always outperform simple composition operators, you mean in large-scale tasks? Like dialogue act tagging and paraphrasing?
Yeah, there, but also for our sentence similarities. And why so? Because there are many decisions still to be done. How do you model verbs? How you build these metrics? We showed you here two different ways, right? Where was here? So here, the two ways to get verb matrices. Maybe that's not really an appropriate way to get verb tensors. But yes.
So can one say that in simple tasks, neural net vectors with tensor composition does best?
In simple task.
For example?
So here, not really, and in the disambiguation, yes.
Yes, okay, right. So it varies. Yeah, thank you.
Thank you for the presentation. So basically, your finding is the neural embeddings have maybe captured the most of the meaning. So as you noted on the conclusion, so is it truly because of the size of the corpus? So if you, for example, for the third task, neural embedding, so used same size as the first task,
yeah.
the BNC, so would the representation or the BNC will be performing same way as non-embeddings?
Yeah, that's a really good question. I think it wouldn't be really fair comparison. Why do you want to use BNC? Because it's a small corpus and you can get distributional vectors easily.
Or the other
What-
ways,
and-
other ways, like for example, have for the non-embedding use the same size, take just random sample, like same size as what you have in the BNC, and see if you can get similar, at least comparable results or not.
But then, to me, all the revolution in word embeddings was that you can scale them to the large corpus. So I agree. There should be comparison on the same data sets, train
Yes.
vectors. But then we would lose the comparison what people have been doing in the past. And we wanted to compare also our methods to the results reported in distributional semantics literature.
I mean, and that's true, that's true. But for your task here, you want to compare which one captures like the more meaning. So in this case, you have to have more or less same scale.
Yeah.
So basically now you are biased toward the non-embedding because you use large corpus.
Yeah, but then if you train the word embeddings in a small corpus, you can say, oh, maybe you get lower quality vectors because of a small data set.
I mean, for sure, probably
Something
yes.
like this,
Yes.
right? So
Yeah,
there is.
yeah.
Thanks.